This is our second video regarding interference of light, chapter 14. In this video, we will discuss Young's double-slit experiment. But before I start, we will discuss the differences between the interference pattern and the diffraction pattern. This is the interference pattern. We have bright fringes and dark fringes. Let us go back to diffraction pattern. This is my diffraction pattern. When a light passes through a slit of order 1 millimeter, the diffraction phenomenon will take place. Here we have the central bright fringe, dark fringe, bright fringe, dark fringe, and so on. Interference pattern and diffraction pattern. Here we have the central bright fringe of the diffraction pattern is double the other bright fringes. This is L, and this L over 2, L over 2. While in the interference pattern, all the bright fringes are equal. So even the central bright fringe has the same width as other bright fringes. The second difference about the intensity of light or the brightness of the bright fringes. In the diffraction pattern, the brightness of the central bright fringe is very high. The intensity is very high. Directly, the first bright fringe at the left and the first bright fringe at the right, their intensities will decrease so much. While in interference pattern, the intensity of the central bright fringe is the maximum and will decrease slowly, okay? And the bright fringe at the right and the bright fringe at the left have smaller intensity of light, but not like the decreasing that we saw in diffraction pattern. Here I have interference and diffraction for green light and for white light. Here the diffraction of the green light, this is the central bright fringe. Here the central bright fringe is double the width of the other bright fringes, and we see that the intensity or the brightness of the other bright fringes decreases so much. Here the diffraction of a white color, we know that the central bright fringe is white since all the lights diffract and the center bright fringe is at the middle, so we get the white color, and also the intensity decreases. While interference, we can see that the central bright fringe and other bright fringes have the same width, and the center of the bright fringes and the centers of the dark fringes are equidistant. We have interference of white color, we will get only the white here at the center, and other colors will interfere at the right and the left. Here I can see the intensity of diffraction with one slit. I have a maximum intensity at the central bright fringe and a very small intensity at the first bright fringe at the right and at the left. While in interference, we can see that the central bright fringe is smaller now, equal to other bright fringes, and the intensity is decreasing slowly. We will start with Young double-slit experiment. First, we will have a source of light. I have two slits. We will denote by A is the distance that separates the two slits, and D is the distance from the slits to the screen that we will observe the interference pattern on it. So we can start here. If I have a source S, we can draw from S to O the perpendicular bisector of A. From S, a light will travel to the first slit S1, and another light also will travel to the second slit S2. Here, S is equidistant from S1 and S2. I mean S1 equal to S2. We will take a point P on the interference pattern, and we will denote X from O to P. From S1, the light continues to P. S1P, we will denote it as D1. And from S2 to P, we will denote it by D2. But we can observe that D1 is less than D2. Then the light traveled from S2 to P, longer distance from the light travels from S1 to P. If we can draw S1B, we can see that S2B is the extra distance that the light traveled from S2. And this extra distance, we call it path difference, delta. Path difference is SS2P SS2P minus SS1P. We can divide SS2P into SS2 plus S2P minus, also we can divide SS1 plus S1P, and we multiply both by minus, so minus SS1 minus S1P. As we said, S is equidistant from S1 and S2, thus SS1 equal to SS2. We cancel them. S2P is D2 minus S1P is D1. We can calculate the value of delta from the geometry of the figure. I will derive it step by step. First, we can see that S1B is perpendicular to this line, and this line is perpendicular to S1, S2. We can see that this angle equal to the red angle, since two angles are equal if their arms are perpendicular. Since theta are very small, because we are dealing with light interference and the angles are very small, what is sine theta of the blue angle? Sine theta is opposite over hypotenuse. The opposite of theta is S2B, which is delta, the path difference. And the hypotenuse, this is the angle 90, the pink one. Then this is the hypotenuse, S1, S2, which is A. So sine theta equal delta over A. I will use this angle theta. We will calculate the tangent theta. So tangent theta is opposite over adjacent. The opposite of this angle theta is OP, which is X, over the adjacent. The adjacent of theta is capital D, the distance between the slits and the screen. For small angles, sine theta equal to theta, and tangent theta equal also to theta. Sine theta is delta over A, and tangent theta is X over D. I can write now delta over A equal X over D, since sine theta and tangent theta equal to theta. So delta is equal to AX over D. By the way, we can use it directly. Delta equal AX over D, you can memorize it. So delta equal D2 minus D1 equal to AX over D. Now let us check. What is the nature of P? Is it a center of a bright fringe, or is it a center of a dark fringe? We can recall that if P is the center of a bright fringe, then the two waves interfere constructively, and we have crest with crest or trough with trough.
If P
is a center of dark fringe, then the two waves interfere destructively and they cancel each other. So crest on trough or trough on crest. A point P receiving two waves is a bright fringe if two received waves are in phase with each other. The path difference is a whole multiple of a wavelength. So delta is k lambda. Of course, k is a whole number, can be positive or negative, or zero. If it is zero, then delta is zero. And here we can see that we are speaking about the central bright fringe. Since S1O and S2O also they are equidistant and they cancel each other, then delta equal to zero. And this is we are speaking about the zero order bright fringe, which is the central bright fringe. If k is equal to 2, then here we are on the second bright fringe, then delta equal to 2 lambda, or it is minus 2 lambda, then this is the second order bright fringe on the negative side. We can write that delta equal to k lambda, and we know that delta is equal to ax over d equal to k lambda. So x equal to k lambda d over a. This is the expression of the position of the center of the bright fringes. If k is 0, then x equal to 0. This is the central bright fringe at O, as in this figure. This is the central bright fringe at O, x equal to 0. If it is the second bright fringe, this is the 0 bright fringe. This is the first bright fringe. This is K1, and this is K2. This is the second bright fringe. Then x equal to 2d lambda over A. X is the position of the center of the bright fringes, and K is called the order of bright fringe. For k equal to 0, as we said, x equal to 0, this is the central bright fringe. For k equal 1 or minus 1, x equal lambda d على a minus or plus, this is the first bright fringe. For the second bright fringe, k will be plus 2 or minus 2 in the positive side or in the negative side. So these are the position of the center of the bright fringes. Characteristics of the central bright fringe. Always, the central bright fringe is the bright fringe having k equal to 0. So its path difference is equal to 0 always, in all cases. Now in case of light rays travel only in vacuum and the source is equidistant from the two slits, as we discussed, the center bright fringe is at x equal to 0. But this one is not always true. We will discuss it in our third video. Now a point receiving two waves is a dark fringe if the two waves are out of phase or antiphase, and the path difference is an odd multiple of lambda over 2. What I mean by odd multiple by lambda over 2, if the two waves are out of phase, then the distance between them is lambda over 2, or 3 lambda over 2, or 5 lambda over 2, 7 lambda over 2, 9 lambda over 2. So we need an odd number, and we know the expression of an odd number. We can use it as 2k plus 1. 2k, I'm sure that it is even. I will add 1, then I'm sure that this expression represents an odd number. So 2k plus 1 lambda over 2, this is the expression of delta, the path difference for dark fringes. 2k plus 1 is an odd number that can be positive or negative. So we can now write delta equal 2k plus 1 lambda over 2, and we know that also delta is equal to ax over d. So we can write the expression of the position of the center of dark fringes, x equal 2k plus 1 lambda d over 2a. K is called the order of the dark fringe, can be positive, negative, or 0. We don't have zero order dark fringe. We have the zero order bright fringe. This is first bright fringe. This is first bright fringe in the negative. We don't have zero order of a dark fringe. We have directly first order dark fringe and first order dark fringe in the negative, second order dark fringe and second order dark fringe in the negative. For k equal to 0, then I will get lambda d over 2a. This is the first dark fringe. And for k equal minus 1, 2 times minus 1 minus 2 plus 1, it's minus lambda d على 2a, which is the first order of dark fringe in the negative side. 2k plus 1 equal to 1 is the first dark fringe. You can check that. To get plus 1, k should be 0. And to get minus 1, k should be minus 1. It's a very important note. In the negative side, k is the order of the dark fringes. K is equal to minus 1, then it is the first order dark fringe in the negative side. K equal minus 2, it's the second order dark fringe in the negative side. While in the positive side, k plus 1 is the order of the dark fringe. Yani k plus 1, for k equal 0, then I will get first order dark fringe. For k equal 2, I will get the third dark fringe in the positive side. If the optical path difference of a point M doesn't satisfy the condition of a bright fringe or a dark fringe, then M is neither the center of a bright fringe nor the center of a dark fringe. Here, because we are dealing with a center of a bright fringe, the center of a bright fringe, or the center of a dark fringe. If the point is not at the center of bright fringe or not at the center of a dark fringe, then it will not satisfy the equation of x for bright fringe and dark fringe. Then it is neither the center of bright fringe nor the center of a dark fringe. Interfringe distance, we denote it by I, is the distance between the centers of two consecutive bright fringes or two consecutive dark fringes. Here the interference pattern, the distance between the centers of two consecutive bright fringes is I, and the distance between the centers of two consecutive dark fringe is also I, interfringe. Let us calculate the interfringe distance for bright fringes. X k plus 1 minus xk. The distance from the central bright fringe, O, this is xk plus 1 minus the distance from this one to this one, this is xk. I mean x2 minus x1 or x3 minus x2. The distance between the center of two consecutive bright fringes is xk plus 1 minus xk. xk plus 1 is k plus 1 lambda d على a minus xk is k lambda d over a. Simplify here the equation, then we will get lambda d over a. K lambda d over a minus k lambda d over a, we cancel it, then we will get lambda d over a. Interfringe distance for dark fringes. To know that, we'll get the same result. Here the same, I equal xk plus 1 minus xk, but the expression for the dark fringe is 2k plus 1 plus 1 lambda d over 2a minus xk is 2k plus 1 lambda d over a. So this is the expression for the distance of the center of dark fringes, 2k plus 1 lambda d over a. Here we put, instead of k, we put k plus 1. 2k plus 2, I have plus 1 also, then 2k plus 3 lambda d over 2a minus 2k plus 1 lambda d over 2a. 2k lambda d over 2a plus 3 lambda d over 2a minus 2k lambda d over 2a minus lambda d over 2a. 2k lambda d over 2a. 2k lambda d over 2a is cancelled. We will get 3 lambda d over 2a minus 2 lambda d over 2a. It is 2 lambda d over 2a. 2 by 2 cancelled, then I will get lambda d over a. So the centers of dark fringes and bright fringes are equidistant.